That's easy, like one remaining.
You may well be caught in the crossfire.
Yeah, that's what I'm worried about. It isn't. Oh, right. Holy spill lower.
There you go.
Hi, everyone. Welcome.
It was on just a second ago. Yeah, I don't know. I'll send something up.
Hello?
Yeah. Yeah, Cliff tested it.
Hello?
It should be on.
A minute ago.
Yeah.
Yeah, I'll just send Cliff. Yeah.
We tested yesterday.
Yeah, just a couple minutes ago.
Oh, okay. All right, I speak loud. So I just want to go quickly, go through, because this application, we are doing parallel sessions simultaneously, both room. Just go quickly about what's going to happen in this room. Go to the next slide. The logistic you already know. The main thing is tonight there is this lab sheets. We can coordinate couples to go to the happy hours, the dinner option. They are nearby. So just sign your name there. We have a lot of drivers. We can help you. Then go down to the next one. Again, we want whoever joined this today. You should either online in person, join the Slack channel. We like to keep this channel active as a community. You guys can continue communicate to the topics we are interested in, not only this workshop in the future, and also we are going to document whatever recommendations you put there. Things like that, we can include that in the report. Yeah, the sessions will be recorded, so we can write the report by listening to the recording, and also made available on the web page if you agree to be recorded. Also, we are going to have the co-chairs going to have a cutoff time for all the talks, and also they're going to take notes so we can have a better report. All the co-chairs, please take notes as much as you can. We are running around, couldn't take much notes. Next slide. So first, we're going to start this session systematic errors. Go to next. Then we have a coffee break. The coffee break, we have a small poster sessions in that room. There are 10 posters. Please go there while you are drinking coffees. Next slide. Then the 10 o'clock is the initialization session, part 1. Then we're going to have lunch. Next slide. 1.5 hours. Then go to the next one is the initialization part 2. Then go to the coffee break, go to the poster session as well. Then after that poster session concludes, we should be ready to select the winner of the posters. So do contribute to that. Then this one for tomorrow, we have a community feedback for SFS. The reason we are doing that, there have been such long time delay updating CX version 2. We really need to get the status of art, science, advice, the experience from other groups. Provide the feedback there. Sorry. Then we have the gap session. That after this, we have a happy hour. Yeah, that's all I have. Thank you.
Sian. All right. Welcome, everybody. As Yan said, yes, we are going to be very strict on time. We're already 6 minutes behind, and this session cuts 10 minutes into the coffee break. So now we're 16 minutes into the coffee break. So, yes. Jonathan Beverley. Oh, is it working?
Yeah.
Excellent.
Oh, it was unplugged.
Oh, we're off to a roaring start. Okay. Take it away.
The mic's not to work right now.
Okay.
Thank you. Yeah, just go back. Start over. Yeah, go back a couple.
How does this? Cool.
Okay.
Okay. Yeah, thank you for the invitation to go talk today. I'm going to be talking about our work recently that we've been looking at trend errors in seasonal forecasts. And this is work that I've been doing at NOAA Physical Sciences Laboratory with Matt Newman and Andy White. So first of all, as I'm sure you're all aware, seasonal forecast models are known to have biases that both develop rapidly and saturate. So the figure at the bottom left here is from a 2012 paper, and this was using the ECMWF model. The black line here shows the observations, and the coloured lines show a number of different initialization types. The red line is the full initialization. And what you see is that for these initializations, the model very quickly diverges away from the observed state into its own climatology. And in this case, in this paper, they linked the fast development of these surface biases to a radiation imbalance at the top of the atmosphere. This figure on the right is from a much more recent paper, and it shows mean biases for a number of different NMME models. 3 different leads, 0.5, 4.5, and 8.5. And again, you see that within the first month, these models have mean biases that have developed, and these kind of fairly quickly develop further, and by the kind of month 4.5, they've almost saturated, and there's not really much change between month 4.5 and month 8.5 in any of these cases. Models are also known to have systematic and rapidly developing errors related to ENSO. So this figure here is from our paper last year, and it shows for October initializations, the regression of the DJF SST error against the ERA 5 Nino 3.4 index. I've got 4 different example models on here, and a couple of different multi-model means. The colors aren't particularly great on this screen, but in the West Pacific, you have a positive regression, and this is associated with an overly extended ENSO SST anomalies in the equatorial Pacific, and this is known to be a common climate model error as well. There are also errors in other parts of the Pacific as well, such as the East Pacific, which is related to either ENSO events that typically too strong or decay too slowly. And again, you can see those in both the multi-model means as well. And this kind of motivated us to examine the similarity between this kind of westward extension error and the same error that you see in climate models. Motivated us to look at trend errors in seasonal forecasts and how similar they are to the errors that we see in synoptic models. So very briefly, as I'm sure you're aware, climate models for a number of years now have exhibited trend errors in their historical simulation of SSTs. So the figure at the top right here shows the observed SST trend over the last few decades. And you can see that in the tropical Pacific, in the central Pacific, there's very little trend, with a stronger warming trend to the east and west of this, and roughly no change or maybe a slight strengthening of the east-west temperature gradient. But the 2 panels underneath show the trends from 2 different multi-model means for climate models, and you can see that the climate models aren't representing this trend at all. You can see that these climate models actually typically project a weakening of the east-west temperature gradient, with greater warming in the eastern tropical Pacific. And a number of potential reasons have been proposed for this discrepancy, and these include things like sampling issues or errors in model internal variability. It's also been suggested that these errors are transient and that over time the observed trend will begin to look more like the model trend. People suggested that the errors could be teleconnected from other regions, such as the Southern Ocean. Errors in forcing fields have also been proposed, such as CO2 and aerosols. Or it could be that this is simply just a model error and the models are getting it wrong some way. But all of these different theories are quite hard to test in free-running historical simulations. But that's where the seasonal forecast models come in, because many of the same or similar models that are used for climate runs are also used to produce seasonal forecasts. So today I'm going to show the seasonal forecast models exhibit systematic trend errors globally, and these are very similar to the trend errors that we see in climate models. I'm going to show these errors develop very rapidly within a month or more of forecast lead time. And I'm going to suggest that these errors likely reflect the sensitivity of the model mean biases to the changing initial condition radiative forcings. So that's as the radiative forcings present in each hindcast run change, this causes the model mean bias to change over time, which leads to an apparent trend error. So I'm going to be showing results from 11 different seasonal forecast models, which are listed here. Some of these from NMME, some of them from Copernicus. And I'm going to be showing analysis over their common period, which is 1993 to 2016. We looked at 4 different initializations, March, June, September, and December. And I'm going to be comparing these seasonal forecast models to historical and SSP245 simulations from CMIP6 models to cover the same common periods, 1993 to 2014 for historical, and a couple of years from SSP245 to cover the same period from the seasonal forecast models. And it's worth noting that while the seasonal forecast models that we use aren't identical to any of the CMIP6 models, they do use the same or very similar radiative forcings to those found in CMIP5 or CMIP6 models. So what do we mean by a trend error in this context? Well, so in this context, we define a trend error as the slope of a linear line of best fit of the model error time series. So model error being model minus observations for a given lead time. And this is the same as taking the difference between the model and observed regression slopes. To help visualize this, I've got a couple of figures here. So this panel on the left shows the preset time series for a given region. This is for Western US. The black line shows observations and the red line shows the multi-model mean. You can see that in the observations, there's a fairly strong negative trend over this time period for this region. But for the multi-model mean, there's virtually no trend. So this would be a positive trend error. The figure on the right shows the time series of the model error. So you can see that, so that's just the difference between these two lines. And you can see that there's a positive trend in the error. And the slope of this line is the same as taking the difference of the slope of these two lines. So the error of the trend is the same as the trend of the error. I'm going to be focusing mostly on seasonal mean trend errors at 2 seasons lead. So therefore averaged over the leads of 4 to 6 months. And we use this particular significance test to compute significance. So we first wanted to look at how the model mean biases in the seasonal forecast model might be changing with time. So the figure at the top here, this simply shows if we take the difference in the mean bias between the two halves of the hindcast period. So to compute this, we calculate the mean bias for the first half, 1993 to 2004, and the second half from 2005 to 2016. And we take the difference in the mean bias in these two periods, and that's what's shown at the top here. And you can see that there are areas of significant bias difference in many parts of the global ocean, including the tropical Pacific, and parts of the Indian Ocean, Southern Ocean, Atlantic. The figure at the bottom simply shows the trend error as I described it before. And you can see that this map here, the colors haven't come out particularly great on this projector, but you can see that the pattern and the magnitude here is very, very similar to the plot at the top here, the mean bias difference. And what this suggests is that the trend errors are representing a roughly linear change in the mean bias, perhaps due to the time evolving radiative conditions that are present in each hindcast row. And as I said earlier, these are the same as that are used in CMIP6 simulations. Another way of visualizing this changing mean bias is shown in the bottom right here. So I've got 2 example regions, so Equatorial Pacific SST and Southern Ocean SST. I should say that both for all these cases, this is for a March initialization verifying in JJA. And you can see that for Equatorial Pacific, the mean bias, this trend error actually represents a reduction in the mean bias over the hindcast period, from a negative bias the first half of the hindcast period to a almost 0 bias at the end of the hindcast period. But in the case of the Southern Ocean, which also has a positive trend error, the mean bias is actually changing sign between the first and second half of the hindcast period. Again, from a negative bias to a positive bias by the end of the hindcast period. So I'm now going to be focusing for the remainder of the talk on the trend errors themselves. So first of all, what I'm showing here is the trend error for the 4 different verification seasons. So we've already seen the one for JJA, which is on the previous slide, but I'm also showing verifying in DJF, MAM, and SON as well. And what you see is that there are significant SST trend errors in many parts of the global ocean, such as the tropical Pacific, the Indian Ocean, Southern Ocean. And you see in the tropical Pacific, in DJF, JJA, and SON, this trend error pattern resembles the El Nino-like trend error that we also see in climate models. And there are also significant errors, as I said, in other parts of the ocean, particularly large trend errors in the Southern Ocean, for example, also in Nino upwelling region, and also, tropical Atlantic, North Atlantic. So and it's also worth noting that the pattern of the trend error that we see across the 11 different seasonal forecast models is very similar. So based on the trend error map here, we then defined a number of different regions, which are shown here as boxes to enable an easier comparison between the seasonal forecast models and the climate models. And I'm showing 4 different examples of those here. So we've got Equatorial Pacific, Atlantic Nino, Gulf Stream, and Southern Ocean SST. Within each of these panels, I'm not sure where the line here has disappeared to, but within each of these panels, there are 4 columns which show the 4 different verification seasons: EJF, MAM, JJA, and SON. And then within each of those columns, the colored symbols indicate different seasonal forecast models, which are listed on the right here. The box plot represents the CMIP6 model spread, and the black symbols indicate 2 other observational data sets relative to ERA 5 to give an indication of observational uncertainty. And what you see is that for all of these indices, the seasonal forecast model spread closely aligns with the spread from the client models. You can see that, for example, for Atlantic Nino, the 2 different model spreads line up pretty well. And it's also worth noting that for the seasonal forecast models, there's often agreement in sign, if not always magnitude, for most of these different regions and seasons. We also looked at other variables. So this is now showing the trend error for 200 hectopascal zonal wind. And again, you see that there are significant trend errors for 200 hectopascal zonal wind. You can see that these are often found in regions near jets. So, for example, in the North Pacific in DJF, or in the North Atlantic in JJA, perhaps associated with latitudinal shifts or maybe an extension of the jet stream in these regions. And there are also other significant zonal wind trend errors, such as in the tropics. This is a pretty large error in SON across parts of Southern Africa. And there are also associated significant precipitation trend errors. I haven't shown the precipitation trend error maps just in the interest of time, but I've got a few different indices shown here. So we've got Western US, Southeast US, Western Asia, and Southeast Asia. And again, you see that there's a pretty close alignment between the trend errors that we see in seasonal forecast models and the trend errors from the client models. You can see kind of for all these regions, the 2 different model sets follow each other pretty closely. The median values from the CMIP6 models often also align pretty closely with the multi-model mean values, which aren't particularly easy to see on this projector. But yeah, they often line up pretty closely. And changes in sign from season to season are also pretty consistent. So, for example, for Southeast Asia, seasonal forecast models go from a negative trend error in MAM to a positive trend error in JJA, and then back to a negative trend error in SON. And this is mirrored very closely by the CMIP6 ensemble. So we then wanted to look at how quickly these errors are developing. So I just put one panel up here so I can explain what's being shown. So this is for a particular index of the North Indian Ocean SST. And on these plots, the x-axis shows the verification month, so January through to December, and the y-axis shows the trend error for the given region. The different colored lines show different initializations. So yeah, which are listed down here, March being blue, June orange, green September, and red December. And the different symbols indicate different lead time. I'm just going to put up the other regions now as well. So I've got 3 SST regions, 2 preset regions, and a sea level pressure region. And what you see is that the hindcast trend errors often follow the same seasonal cycle and are kind of have a fairly strong dependence on the seasonal cycle. For example, for Southern Ocean, you can see that the trend error typically peaks in the Southern Hemisphere winter and has a minimum in the Southern Hemisphere summer. And this is also seen in other regions as well, such as North Indian Ocean. You can see that the lines tend to follow each other, maybe slightly less so for Equatorial Pacific, but it's still the same sort of pattern. And for the precip and sea level pressure indices, this dependence is actually even stronger. For example, you can see that for the first month of the September initialization for Southeast Asia, the magnitude of this trend error is very, very similar to the trend error that we see for the 4th month of the June initialization. So really emphasizing that these trend errors are very closely tied to the seasonal cycle. And the fact that the trend errors are perhaps more closely tied to the seasonal cycle for precip than they are for sea level pressure may indicate that these errors are developing in the atmosphere and reaching something closer to saturation there, whereas the SST errors may still have a slightly slower spin up and haven't quite reached saturation there. So that brings me to the end. Hopefully I'm doing okay with time. So I've shown that seasonal forecast models have significant trend errors that develop very rapidly within 1 to 2 seasons of lead time. I've showed that these trend errors are very similar to the trend errors that we see in the historical climate simulations. And I've suggested that these trend errors that we see reflect the sensitivity of the model mean biases to the changing radiative forcing. So that is, as the radiative forcing that are present in each hindcast run change, this causes the mean bias to change over time, which leads to the apparent trend error. And as I said earlier, it's important to note that both the initialized and uninitialized models contain the same historical external forcings, which might be one reason why the climate models and seasonal forecast models have such similar trend errors. And as these forecasts are initialized from observations, this suggests that the trend errors that we see in climate models aren't due to unrepresented internal variability or transient, but fundamentally they are model errors. And I'm going to end with a plea for anyone that's involved in the production of hindcasts. One of the potential limitations of our study here is that we had a relatively short common hindcast period from 1993 to 2016. We did test the sensitivity of our results to this, and it didn't seem to make too much difference. But still, it would be very nice if we could have longer hindcast periods, maybe 30 or 40 years, which would enable us to generate a much more robust analysis of these hindcast trend errors. Thank you.
Thank you. That was great. We actually have time for questions. Bill.
Great presentation.
I think there's an emerging consensus that the equatorial Pacific SST trend errors in CMIP models, et cetera, are real, but in general, you showed sort of 5% significance of trend errors over the globe, and so we would expect that over 5% or so of the global area there would be such significance. So in that framework, do you think sort of all of those crosshatch regions are actual trend errors and not just kind of a sampling?
I think so, yeah, and I think also the trend test that we use is perhaps quite strict, particularly when looking at a shorter time series. So it might be that there's actually larger areas of significance than maybe the fairly strict test is showing. And also when you look at individual models, you do see possibly, certainly in some models, you see larger areas of significant trends. Perhaps indicate, yeah, there are kind of more real trend errors, I guess. Yeah.
Okay. And the Canadian models do have hindcast back to 1980, by the way, on the IRS.
Right. Yeah. Some of the models that we use, yeah. So like the CIS5 as well goes back to 81, I think. But yeah, because we wanted to do a multi-model mean analysis of compare all the models, we had to kind of trim it down to the common period that we have.
All right. Thank you, Jonathan. All right. Our next speaker is Andrew Wittenberg from GFDL.